Okay guys, I'm just talking about the simple. Let's imagine. See, I'm just taking one input and one output because it's easy to analyze. But in reality, you might have multiple inputs. Okay, so three-dimensional, four-dimensional, five-dimensional. What do I mean by three-dimensional, four-dimension? For example, X is say your engine type and Y is your price, right? Now, depending on the engine, your price is changing. So this is your input. But in reality, your output is also dependent on other features, right? For example, the shape of the rear mirror, or for example, how well efficient you have, like which kind of tires the vehicle is using. So there are different input parameters, right? So what I meant is there can be multiple inputs such as x1, x2 and x3 so on, but our output is y. But let's take for simplicity only one x and one y. So in this case, for example, x comma y is somewhere here, x comma y is somewhere here, x comma y is somewhere here. So there are different data points which I have, right? Now by these data points I should train my algorithm so that in future, for example, there is a one future data point which is here. I want to predict what is y for that, right? Oh, sorry, not here. Let me just do that. Your new future point is somewhere here. X is the x value is somewhere here. Okay. So you have to correspondingly you have to find what is the y for this, right? So now the point is for this data points or the these are the black points are historical data points on which your model will get trained. Let's say this is your future data set. So okay, this is new terminology for you guys. When your algorithm is on the data on which your algorithm gets trained, that is called training data set. Remember guys, and any new data for which you do the prediction, that is called test data set. Different people have different terminologies. They call it as training data set, test data set. Some people call it as train data set, validation data set. Some people call it as dev data set, future data set. Some people call it as train data set, dev. Some people actually split them into three: training data set, dev data set, and test data set. So you don't have to worry. The logic is same. The concept is same. Okay. So now, for example, here for these data points, I can have multiple linear lines because we are working. The first algorithm of machine learning which we'll be looking at is linear regression, right? So there can be multiple linear lines, right? So based on these multiple linear lines, the value of y will be changed. It will be different for this x value, right? If for this line, the value of y might be somewhere here. For this line, for the corresponding x, the y might be somewhere here, right? So it's not simple. We have to come up with the best linear line, right? Because we can draw any infinite number of lines which actually passes through these different data points. But the line which is called as best fit line or the best line across this data, for example, this is your best fit line. There will only one best fit line, and that will be calculated based on the errors. Errors in the sense, for example, your data point was lying here. It was here, right? Let me do. Okay. And of course, there can be some points which will be exactly on this line. So for this corresponding x, there will be some y, right? Which is y actual. Let's assume for this point, if this is x, for this point, this would be y actual. But what will be y predicted for this point? Y predicted would be the arrows should not be in this direction. Okay, let me draw it once again. For example, this is your data point. The error will be always calculated perpendicular to the x-axis because, for example, let's take, this is your point, say x1 comma y1. Let's say x1 comma y1, this to be x2 comma y2. Let's take some example. So these y at these points are the your y actuals, right? But with this linear regression, for this corresponding x, your y is somewhere here. So this is your y predicted. Okay. So your error is calculated between y actual and y predicted. Okay. And how do we calculate that? So it's a simple Euclidean distance formula, or the distance formula which we have learned in our school days. What is the distance formula? Or let's take this one, because x is same, the error would be sigma of y actuals minus y predicted whole square. Simple, right? So for all the data points, for example, if you have 5 data points, then this n value would be 5. And then sigma would be repeated for 5 different data points, for which you will subtract ya minus yp and whole square it. Okay, this is called as root mean square error. Okay, so there can be infinite number of lines through these data points, but there will be only one line which will be having this minimum error. When you have achieved the minimum error for particular line, that is called as best fit line. And this best fit line will have a linear equation, right? So whenever there is a, as we all know, if there is a linear equation, whenever there is a new data point, just put that x value in the equation and find out y. Okay, so it's straightforward. It's a very simple thing. But now the important thing which I want to explain here is, there are different ways for calculating error. There is something called as mean square error, which is 1 by n sigma ya minus yp whole square. There is something called as mean absolute error. Okay, in this case the error is calculated in this way, modulus of ya minus yp. So there are different ways for calculating this error. Okay, making sense, guys? Now see, and we know that the best fit line will have the minimum error, right? You can use any error formula, but the best fit line should have the minimum error. Making sense? Now this is where your mathematics comes in again. If we could recollect, guys, from your college days, if we want to minimize something or maximize something, what do we used to use? I think I have already answered your question, no? How are we choosing best fit line? The line which has the minimum error. But yes, I got your question. How are we choosing? It's not straightforward, right? We cannot keep on calculating errors for different lines. We cannot do that, right? So there has to be some method which actually chooses the best possible line, right? So how do we do that? So as I already told, we have to minimize the error. So could you please tell me what is the concept which we have used for minimizing and maximizing in our college days? As we are calculating the error for different lines, we know the best fit line would be the one which has the minimum error. And if we want to find at what point we will have the minima or maxima, what we used to do, guys, in our college days, we have to differentiate, right? Using differentiation. So here also we have to use differentiation, for which there is an assignment which you have to work on, guys. I'll just give you the mathematical intuition. So for example, let's take a very simple line equation. This is called as simple linear regression. When we have one input and one output, it is called simple linear regression. When we have multiple inputs, then it is called multiple linear regression. But as I told, I will explain the concept for simple linear regression. You can always extend that for multilinear regression because the concept is same. So see, in our school days, what we used to do, we used to get the line equation, we used to substitute the values of x and get the values of y, and then we have to plot the graph, right? But now we have grown up. Now the problem is difficult. What we have is, we have different data points. We have x and y. We have to find beta naught and beta 1 such that the error is minimum. That is what we have to do. And that is where we have the challenge now. You're getting my point. So just imagine in this case, say this is your beta naught, say this is your beta 1, and there is a third dimension which is called as, say, error. Okay, or let's say this is your error, and this dimension says, let's say this is your beta 1. Don't get confused, it's a 3-dimensional. So when you draw the graph between this different beta naught and beta 1, you'll get the different error values, right? So this error needs to be minimized. For example, for this beta naught and beta 1, let me take some other color. Yes. So for example, for this beta naught and beta 1, the error is so high. Okay. And how we are drawing this graph, it is important to understand. Now we have to slowly move down. How do we move down through the graph? Through tangents, right? And how do we come up with the tangents? By derivation, right? So we are moving along this graph. Okay. And this is where you have the minima, right? So if the error is minima, for which particular beta naught and beta 1 your error is minimum, we will take that beta naught and beta 1 and that will be considered as your best fit line. So far so good. But how we are moving down? How can we make sure that we are moving down? For that, there is a concept of tangents, right? Remember from your school days or college days, how do we calculate the tangent? By differentiating. And what we have to differentiate? In this case, I have just written y, but in reality, what we are differentiating? We have to differentiate the equation what we need to minimize. And what we need to minimize? The error, right? So we have to minimize error with respect to beta naught, and we have to minimize error with respect to beta 1. Okay. And what is the error equation? For simplification, we can use this error equation. Now you must be wondering, where is x here in this equation, right? Actual value is already given. The predicted ones would be based on this. Okay. Okay. Substitute that yp in this error equation, and then you have to differentiate. And once you differentiate, what you will get? You will get tangents, right? So by that you will get and slowly you have to move down, and by that you will get the minimum value. Okay. So now I have given you the mathematical intuition behind how does this minimum thing, what we are trying to minimize, how does it work? And whenever you are trying to minimize or maximize something, that is called as gradient descent method. Okay. In our case, we always try to minimize something because we are minimizing the error. Okay. So this is important. This is our error function, and this is what we are trying to minimize. Okay, guys. This is also called as your loss function, or this is also called as cost function, but you don't have to worry much about the terminologies. This you will learn it slowly, all the terminologies, but the important thing is what we are trying to minimize. We are trying to minimize this error, and this equation is called as cost function or loss function. So there is a slight difference between cost function and loss function, which you have to work while reading. You have to come to know what is that difference, and you can tell me in the next session what is that difference. But that is not important for me. The important thing is we are trying to minimize mean square error using derivatives, and that this derivative method is called as gradient descent method. Okay, guys. So you got the logic, you got the mathematical intuition, but in coding, you don't have to do this much. There is one simple line of code which will give you best fit line. But as I always tell, don't go with the one line of code. Understand what's happening at the back end, right? So for example, I have different inputs, x1, x2, so on. And this is my value y. Okay. Now the reason why I have written e is, so for example, this is your x1, y1, x2, y2, x3, y3, x4, y4, so on. For corresponding x1, there will be y actual. But what we are writing here is y predicted, right? This linear regression is for predictions. This will be y predicted, and it will have some error, and that error is by this line, right? It is shown by this line, right? Making sense? Now, this all are okay. We are coming up with the best fit line, but how do we evaluate whether the best fit line what we are getting, is it good or not? How do we evaluate? So for that, there is something called as coefficient of determination, which is also called denoted as r square. So for example, if r square is say near to 1, that means it is the prediction what we are making are with very good accuracy. If the R square is lesser than 1, for example, say 0.7, then the predictions what we are making, it might not be very near to the actual values. Okay. If the R square value goes further down, then it is actually the accuracy of the model is even going down. Okay. So we have to make sure that the R square is always near to 1, but sometimes it's not easy to bring your R square value to 1. It's not very straightforward. So the assignment or the challenges what I have given, in this case, you just need to you have to come up with a linear regression and then you have to evaluate the R square. You don't have to improve the R square value in this course. We will see how to do that in the coming sessions, but now, as of now, you don't have to do that. Okay. But the important point is R square it's a measure for validating or evaluating your linear regression model algorithm. How well your linear equation will predict the output for the given inputs. Simple. I'm just using simple English words here. Okay. Making sense? I'm just using simple English in my course so that you all can understand. So this is what I was talking about, gradient descent. This is my mean square error which I was talking. If you remember, 1 by n sigma y actual minus y predicted. And what is your y predicted? This is your y predicted. I have substituted that here. Instead of writing beta naught and beta 1, I have written mx plus b. Instead of beta naught, I have written here beta naught is b and beta 1 is m. No confusion, right guys? It's just replacement of that coefficients beta naught and beta 1 with m and b. Now I have differentiated the error with respect to m and then with respect to b. And then I am moving from one point to other point to find where is that point for which the error would be minimum. You can always keep on moving, but then you will notice at one particular point, your error, initially it might be increasing, but at one particular point, your error might start increasing. Okay. So initially your error might be decreasing, but at one particular point, you might notice that your error is increasing. And that is where you have to stop, guys, because that gives you a hint that the error is minimized at that particular value. Okay. And then, so how we are moving on to that particular tangent? By using these values. For example, what is this? This gives you the tangent, and the tangent might be, say for example, for this curve, the tangent for this point, say the tangent is this much. So now the tangent can be this much, the tangent can be this much, the tangent can be this much, right? So how do we ensure that we have to slowly move, right? How do we ensure that we have to move slowly? So for that, there is something called as learning rate. So we have started with some random values of b and m. We got some error. We have taken that one big tangent, but we have to make sure by using the learning rate, we are not going far. If we are going far, then we are going away from our destination. So we have to go slowly. So ideally, learning rate, in most of the cases, learning rate will be 0.001, but it depends on the problem again. Okay. If with 0.001, your learning rate, the error is increasing, then you have to reduce it further. So what we are doing, using tangents, derivatives, we got the tangents. Now we are updating b and m again with some smaller values of learning rates. Now we are here. And then again we calculate error. Okay. Then again, by using this error, again we calculate this derivatives. Again, this using derivatives, we again calculate b and m. So we are updating our b and m value. So now suppose you are here. So you have to take tangents again, and then your point is here. So you have to keep moving. And then at particular point, you will notice that the error is minimized. So that is where you have to stop. And that particular b and m value would be your final value, which will be used for your predictions, mx plus b. So once you get the final m and b, so this, your y prediction is trained now. Your output is trained. Now, whenever you get a new x value, you just need to substitute here with the same value of m. Say x is some new x new, which is a test data right now, because we have trained the model on training data set. Now x new, and now you have to predict a y value for this x new.